look at optimization problems today. Right? Optimization problems. So we're going to optimize something. That just simply means finding out the min and the max. The min and the max, so the maximum amount of something, the minimum. When you optimize something, say in business, you're trying to find the maximum revenue you can get, or maximum profit, I should say, you can get with minimal cost. Something like that. All right, so that's all I mean by optimization. Now, on the first one here, and a lot of times the diagram will help on some of these. It'll be the same idea as the related rates. Sometimes the diagram's helpful. Sometimes you have a known formula. Sometimes both are helpful. Right? All right, so on the first one here, we're going to construct a rectangular pin. We have 300 feet of wire. 400-foot long chicken coop will be used to form one side of the pin, so no wire needed. So, all right, here's what we've got. We only have 3 sides we're working with, right?
Yeah.
Yes.
Yeah. That coop's on the other side, and the fact that it's 400 feet really doesn't matter. I guess 400 is going to be more than this anyway, so it's stretching out. So the way it's written works, but you can also think of it as, you have a rectangular backyard, you're going to put a fence around it, but you're going to use the house as one of the sides. So you wouldn't actually fence along the house or something like that. Right, pretty basic. All right, we have 300 feet. What I don't know are the dimensions to use for the 300. So I'm going to call this X. That means this is X. Well, how do I know they're both the same?
It's a rectangle.
It's a rectangle. Okay? So that means that the third side would be 300 minus 2X. You've done this in algebra before.
Okay.
Yeah.
Just gotta make sure.
Yeah. Everybody okay with the 300 minus 2X?
Yes.
Minus what it already used. All right. So we are trying to, how can the pin be constructed to have the maximum space? So that would be maximum area, right?
Mm-hmm.
Right. So area of a rectangle is length times width or base times height. However you remember it. So in this case, A of X would be X times 300 minus 2X, or A of X would be 300X minus 2X squared. Does that look all right to everyone?
Yeah.
All right, so here's what you did in the past. Okay. Kind of mix some things in here. So from your old algebra class, what's the shape of that graph, 300x minus 2x squared? Parabola, which way is it opening? Down. So since it's a parabola opening down, it makes sense that it would be a max, right?
Yeah.
That max points at the vertex. Everybody agree?
Yeah.
Okay. So here's what you did back in algebra. You need the vertex, because it's an upside down parabola. Do you remember the old vertex formula, or sound familiar? Negative b over 2a?
Yeah.
Sound familiar? All right, so here we go. Negative 300 over 2 times negative 2. 75? Yeah. So that would be the x coordinate, right?
Yeah.
So now the question comes in. Were we asked for the maximum area or the dimensions?
Maximum.
The dimension, right?
Area.
Maximum space, so it'd be area.
No, it says,
Then how can the pen be
how can it be constructed? That would be the dimensions. So in other words, we need to know what these lengths are. How would we construct it to create that max area? Does that make sense?
Yes.
Now, if you wanted the max area, we just substitute 75 back in here. Everybody agree?
Yeah.
You'll get whatever that is. But anyway, for this, the width would be 75 feet. The length would be 150 feet. Or you can call it base and height, doesn't matter. I'm just more used to length and width. right?
Yeah.
Yes.
Okay, here comes the calculus part.
Yeah.
I'm gonna go back to this a of x that we did develop. We still got to develop the equation we're gonna use. So 300x, forgot my x there, minus 2x squared. Okay. The max on a graph. What will be the slope of the tangent line at the max value on a graph?
0.
0. At a max or a min, right?
Yes.
The relative max or min, the slope of the tangent line is going to be 0. And we've talked about that over and over. So if I want to know where that's going to happen, I look at the derivative. 300 minus 4x is 0. X is 75. I know the slope of the tangent line at any relative min or max is 0. So let me find the derivative, which is the slope of the tangent line. Set it equal to 0 and solve, and I'll get 75 for x.
You can still do it either way.
You can still do it either way. But this is something we've been talking about, isn't it?
Yeah.
This isn't new. Now we're going to use this idea. So this would be width 75, length still 150. Now on this problem, yes, you can still do it either way because we know it's an upside down parabola. We know how to find the vertex of the parabola, everything else. But it gives us a good example of how the two tie together and the fact that slope of the tangent line is what's important. That's where it's going to be 0. Right? Now think about something like this. You don't need to write this down, but you would actually have two spots on this cubic where the slope of the tangent line is 0, right?
Yeah.
Okay, well I need this guy, or I need this guy, and guess what's not going to work? A vertex formula, because it's not a parabola. So this vertex formula, yeah, it's nice. But oddly enough, it only works on a parabola because it's a vertex. It's not going to work on anything else. So that derivative comes in handy working with all types of functions. Whereas true, back on this guy, this works great and it will work every single time. Because it is that parabola, it is a vertex we're talking about. And I'm not going to say don't use that, but this is where we're kind of showing where this was a basic piece we needed a formula or something to kind of figure out. Now we're using that idea to develop something for the future on everything else that we use for that piece. Are you okay with that?
Mm-hmm.
Question?
How would we solve specifically for a max or a min?
To determine if, so in other words, like on this where you get two answers, you'd substitute it back in. Which one's going to produce the bigger one? The bigger one would be the max, the smaller one would be the min. So let's say we had something like this and we get two x values for the answer. Let's say the x values are 3 and 7. Well, let's find out which one's going to produce that max, the 3 or the 7. That's what we would do, because we can still figure that piece out. So let's look at the second problem there. Read through the second one. I'm just going to put a diagram up here. All right, so we've got this rectangular sheet, 24 by 45, and what we're trying to do is take the corners out. So we want to take enough of the corner out on each piece. Give you an idea here, so that you can fold up the sides and start creating the box. Does that make sense? All right. And since it's going to maintain the fact that it's a rectangle, we got to make sure each of the corners coming out is the same. It's going to create something like this. Are you okay with that? All right, so each one of these guys have got to be the same coming out. So we're going to take out an amount here, and here, here, and here. And that will fold up our ends, and we're going to see, all right, how much should we take out to create that largest volume? Well, it's going to make the largest volume. So obviously, the more that we take out, the taller the box piece is going to be. The less we take out, the shorter that box piece is going to be. But what determines volume is how much it holds, right? So we got to figure out how much to take out for that. We don't know. So we're going to take out X. But I'm taking out a square, so I know it's an X by X squared. Is everybody okay with that? So that's going to make my dimensions on this bottom. For my final box piece, 45 minus 2x and 24 minus 2x. Because you've got an x on each part. Taking out x and x.
Why would it be 2x as opposed to x squared?
Because you're adding them together is how much you're taking out, or subtracting both. All right. So, I don't know, I'll make something up here. Let's say I take out 3 and 3, but remember the total was still 45. So it'd be 45 minus 6, not the 3 squared, 9. Taking off each end. All right, how do you find volume of a rectangular box? All right, length with height. So in this case, length, I'll write them out here, 45 minus 2x, width, 24 minus 2x, height, x. Are you okay there? All right, so let's get our volume function. V of x would be 45 minus 2x times 24 minus 2x times x, and we've got to get that all multiplied out there. Some of you have these really worried looks on your faces. You do have a calculator. Multiply those.
It's higher than you.
Oh, so, okay, yep. It's like 10%. Okay.
And there's my equation. See if you agree with that. Everybody agree with that? Thank you. Okay, so we're trying to maximize or minimize here, and we're trying to find the dimensions for the maximum volume. Okay, so that means I need the derivative. So let's review. Why the derivative? Because the slope of the tangent line at a max has to be 0. Slope of the tangent line is the derivative. So if I figure out where the derivative is going to be 0, then I'll know the x value that's going to produce that max. Are you okay with that? Okay, so let's look at the derivative. V prime. Let's see, 1080 minus 276x plus 12x squared. Are you okay with that? For my factoring piece, this is where I need to factor quadratic formula. solve or something like that. But I've got to get this thing solved. I know that for most of us, myself included, I'd probably rather have the x squared term on the front. So I know for me, first thing I would do would be turn it around, because I'm used to having that x squared on the front. I can actually take a 12 out of here, I do believe. Yeah. So I'd have x squared minus 23x plus 90 all times 12. I can factor 12 out, and the 12 is not going to matter in the solving. I mean, I can divide both sides by the 12. There's no x sitting out there. So that inside, x minus 18, x minus 5. 18 times 5 is 90 and gives me 23. So now x would be 18 or 5. Now the question came up earlier. Well, if we had some sort of cubic graph, and this would be that cubic graph where you had a max and a min, hey, we're going to end up with a couple of x values. How would we know which one's correct? Right, now we've got our two x values. One of those on the graph will produce where the max is. One of those on the graph will produce where the min is. We want the max. Okay? So this comes back to that real world domain. We're building a box here. Okay? In the real world domain, 18 is impossible. It's not impossible as a point on the graph, but it's impossible for the box. Why?
Because 24 minus 36 is not.
There we go. Well, yeah, we can't have a negative width. We're not doing inner space. We can't have a negative width. So the 18 wouldn't work in this case. But the 5 would. So now I can find my dimensions. That means the height's got to be 5. 5 inches. The width, 24 minus 10 would be 14 inches. And the length, 45 minus 10, 35 inches. Produce that max volume. Are you okay with that?
Yep.
All right, so Drew is helping us. All right, let's look at the back side. 3.
Ooh, I love these kinds of problems.
Read through 3. Just getting this erased here. All right. 2 positive numbers whose product is 16 and whose sum is a minimum. All right, first off, I don't know what the 2 numbers are. I mean, I can come up with all kinds of numbers that will multiply to give me 16. Okay. At this point, I don't know what they are. So I'm going to say x times y is 16. I'll just call one of them x and one of them y. You call them a and b for all I care. It doesn't matter. Just variables. And then whose sum is a minimum. So I'm just going to say sum equals x plus y. That would be the sum of the 2 numbers. I go through and kind of work this. Now the idea would be minimum. The word minimum, you can circle that word. That means there's your optimization. You're trying to minimize or maximize something. That's the optimization. That's what you're trying to optimize. So there's my clue. And it says that the sum is a minimum. If I'm going to optimize the sum, then this becomes the differential. Are you okay with that?
Yeah.
So what I need is sum prime. I need that piece. You can just put that down as just S, but like I've said before, my S's start looking like 5, so I don't usually like to use S's. So I need that differential for the sum. Now the problem is, I've got two variables sitting there, x and y. Be a much easier derivative if I only had one variable. So what I'm going to do is trade y out. Sum equals x plus 16 over x. I can solve this for y. That x over, right? Okay. Now this goes back to what we talked about before. When I first look at this, and I need this sum prime, I have three variables, sum, x, and y, which is going to give me three differentials. I want sum prime. The derivative of x is 1. That's not a big deal, but I have no idea what dy dx is. For thinking back to that implicit differentiation we've done before, which means I've got to get rid of y. I don't have any clue about a dy dx. So I'm getting back down to that one variable, or I should say two variables, because I still have the sum here as 1. So here comes my sum prime. 1 minus 16 over x squared. Be that sum prime. Are you okay with that?
Yeah.
Now remember that 16 over x? Quotient rule. I usually think of it as a power rule. 16x to the negative 1. There's where I'm getting negative 16x to the negative 2, and then just take it back down.
Wait, so wouldn't that still be plus 16 over?
Negative 1 comes down. Negative 1 times 16 is negative 16.
Oh, I see.
All right, now if we're going to minimize or maximize, what does the derivative have to equal? 0. Everybody agree with that?
Yes.
All right, here we go. 1 equals 16 over x squared. I move that over, at least I get rid of the negative. Multiply both, x squared is 16. X would be plus or minus root 16. So x is 4 or negative 4.
Or if you lose the negative in front of the 16 over x squared.
I moved it to the right side.
Oh,
Solve the equation. Everybody okay there?
Yeah.
Okay, I'm going to throw out the negative 4 and keep the 4. Why?
Because it says
Positive.
positive.
It says positive. In the instruction, it says 2 positive ones, so that's going to eliminate that negative 4. So in this case, x would be 4, and also y would be 4. Since x times y is 16, if x is 4, that's going to leave a 4 for a y.
So how would you find the maximum?
Good question.
Where the sum would be a maximum.
The sum would be a maximum. Yeah.
You still work the same, but you wouldn't end up with a positive on that piece here. We'd have to have a different piece up here.
Gotcha.
It's going to change out on each one. Okay, what I want you to do, skip number 4, read through 5, and draw a diagram if you need or what have you. don't care how you draw the triangle, I just don't know what theta is. I don't know what the angle between is. I know two sides are 4. I don't know the other piece. I do know this. Area of a triangle is 1/2 base times height. So, if it's a right triangle, you have a base and a height. But right now, I don't know anything about that. I'm just trying to figure out where that base and height would be. The altitude of the triangle would be the height, form with the base. So picture this, as this angle is going down or moving up, it's changing the height. Everybody okay with that? Okay. The base would never change, it was locked at 4. Because that was the side of the triangle. All right, but the angle is sitting there going down or back. That's going to affect this guy. Everybody okay there? All right. So let's get our formula here. Areas. 1/2. All right. Base is 4. I've got that piece. The height would be 4 sine theta. Here's where I'm coming up with the height. First off, I'm asked to make area large as possible. So I've got to have my area formula. I need my A, or in this case, it'd be A of theta. I just didn't write it like that. But I need my A. I need that piece. As far as the height, I'm asking about a change in the angle. What size does the angle have to be? So I can't deal with both of these variables. I've got to have just one of them. The base was easy to get rid of. It was a standard 4. Not changing. But putting a height in, if I just left it like this, then I don't have any information regarding the angle. And it asked me what should the angle between them be. So I need to have theta in there. Is everyone okay with that? Now as far as the 4 sine theta, back up there where that came from. I'm looking at my triangle here. Opposite, hypotenuse. So H is the opposite, 4 is the hypotenuse. What the hell, if I can pull it out this way, here's that H. So there I'm seeing, there's that opposite over hypotenuse off of SOHCAHTOA. So that means the sine of theta is H over 4. There's where I got H is 4 sine theta. Everybody okay with that? All right, I can clean this up a little bit. A of theta would be, let's see, that's 2, that's 8 sine theta. Half of 16 is 8. Now my derivative. A prime. All right, what's the derivative of sine?
Cosine.
Cosine. So 8 cosine theta. Throw the inside chain, still 1, not going to change anything here. We're optimizing it. We're going to look for where that's 0. So I can actually divide the 8 over, it's not going to matter. So I'm looking for a cosine 0. And where would cosine be 0? At pi halves. Or 90 degrees. Theta would be that pi halves. Are you okay there? Now, I know technically on the unit circle, whereas cosine 0 would be pi halves and 3 pi halves. But at 3 pi halves, it's kind of tough to make a triangle back there. But then if you made it this way, guess what? That's still pi halves. Back the other way, so it would still be that pi halves angle. Right. There, 3 pi halves is too big for a triangle. You only have 180 degrees to play with. 3 pi halves is 270. So that's what's going to take me to that piece. Are you okay there?
So pi halves, that's 90 degrees.
Right.
Oh, okay.
All right, your homework. Okay. Give your homework. Here's a couple formulas that will help you with your homework. We already talked about a rectangle being length times width area. Parameter is 2L plus 2W, or add up all the sides. That should sound familiar. Okay. You'll also use a distance formula, I believe, on one of them. So I'm going to put that up here. Distance formula is one of those things that by the time you get to this level, you kind of forget about it. You know it, but it's just been so long since you last used it. But the distance formula was just really that old Pythagorean theorem, changing x and changing y. Okay, so I get that one down. All right, and let's see how you do on these.